recording? We're good. Okay, cool. So TensorFlow, we're building back TensorFlow. So about me, I like everything. I have insane interest in everything from like physics, games, to whatever you can think of. Actually, what inspired me to actually build this proof of concept with libraries, I wanted to build essentially a physical chemistry library. Fun facts, I love disc golf. Super fun. I have dogs. I'm a terrible speller. And yes, I love dad jokes. So if you want to hear one, come to me after the thing. So kind of like what the reason why GPU computing. So a lot of it has to go back to my past when I was just essentially doing a senior thesis. And my coworkers and I would fight over, CPU cores to do these massive computational simulations of proteins. It would take weeks. And I was lucky if I got something like 6 cores on this cluster, and it would take weeks to do something like several nanoseconds. Thinking back to those days, it would have been much nicer to do something with GPU. Because you have so many more threads where you can update so many more coordinates all at the same time. It's just much better for, it's much better for simulation work and getting a lot of throughput using the GPU. However, given that using GPU compute is not always the fastest thing, if you are into latency engineering, part of it is you have to take into account transferring memory from the CPU to the device, which is your CUDA card, and transferring it back. And there's a lot of setup and a lot of things going on in the background that makes things slower. So, it's not always the best thing for every application, but for doing, if we're doing some simulation work, it's actually works out quite well. All right, on to this TLDR. What did I say here? Yes, crappy TensorFlow. So I guess I'll go over some reasons why you may want to do this. A lot of people don't like C++. That's just unfortunate. I love it. But a lot of people who are scientists or people who do data modeling don't want to deal with the hassles. They don't want to deal with this low-level systems. They just want to get to the math. So by giving them a nice little user interface like Python, it makes life a lot easier for them in some ways. Now, the thing that really that I really wanted to do originally before talking about Python is I wanted to use the latest and greatest version of C with CUDA. And the thing is that CUDA's compiler only supports all the way up to C++ 14 and has a very limited feature set. At times it feels like I'm like a Neanderthal hitting the CUDA compiler with a rock trying to get more C++ features. And that's in a way, that's what the hacking kind of helps us do, is to really maximize our use of C++ while getting the GPU support. So get your cake and eat it. And then the other piece is that that I found interesting is when I got to C++, I learned a little bit about templates. I'm like, ooh, I'm excited. But then I realized that you can't use templates if you're making shared libraries. So a lot of people, if they do use templates, they do one compilation unit, and it just basically creates your executable from that. So I'm going to basically show some hacks about how I kind of got around that. So I want to basically show you a demo of what I built in my spare time. And let me throw up this stuff. And I'm going to basically just show you the what I did. So basically, this is a regular Python runtime thing. I'm profiling C++ and NumPy. NumPy's way faster. This is of course just a proof of concept. So here I create basically a 1 megabyte array, and then I basically write it to the device, compute something, and then write it back to the host and return it into Python, and I return the value, and NumPy does it within the CPU.
Hey Taylor,
Yeah.
can you do me a favor and make the, if you can, the text a little bigger?
Yeah, absolutely. Oops, I did something wrong. Let's see, I think I can zoom in. Control plus.
There you go.
Is that good enough?
What do you think? In the back row, can you guys see it?
Yep.
All right.
Awesome. Cool. So this is essentially just a simple proof of concept. And hopefully it works. So yeah, the CUDA stuff is a lot slower. But what's really cool is we can kind of analyze why. Because the way that I set this project up, not only do we build out the the libraries, but when we build tests as executables, we can actually run a CUDA profiler against it, and it gives you basically a breakdown of all the profiling information that you probably would want to make something go faster. So that's the demo, and we'll go into the code later.
Hey Taylor, can you back up and show us a little bit more about the demo? Like, for example, what were we looking at?
Yes, so what are we looking at? Okay, so what are we looking at?
This is like your output there. What are the numbers? What's it telling you?
Oh, thank you, yes. Let me go ahead and do that. Oops. It's between So what we're looking at is the value of the dot product. What we've done is in the script here. Let's see. Where am I? Oh yeah, run.py. So here what we have is we have 128 times this one that shifted over 20. So this creates a shape. So just to make things simpler, this creates an array of 1 to the 20 shifted elements, or 2 to the 20 elements. That's what this thing does. So it creates that on the host. Then we fill it with a decimal point 2.0, and we say that the type that we're using is going to be a NumPy type of float 64. Normally, if you're doing machine learning, you're always going to work in something like in floats, floating point numbers. I've never seen anyone do integers, to be honest. But and then here, this is calling into C++. CT dot is the library that I built. And so what it does is it creates, it basically writes it to the device, runs it. And so I'm also outputting the time it takes in nanoseconds. So so you can see clearly that the two values match up. I'm going to assume NumPy's right. So I'm going to assume that I'm right too, hopefully.
So your CT dot is where you're offloading it from to the GPU.
Exactly. We're transferring the information from NumPy, Python into C++, and the C++ then transfers that data from the host, being the computer, into the device, being the video card, and then it runs the kernel, which is what actually does the dot product for us. Dot products are really interesting in this case because it allows us to demonstrate several different concepts within CUDA. It's essentially a MapReduce like function, and I'll show you how all that works within CUDA, which is going to be really cool.
Quick question. Have you tried running that with like 32-bit floating point? Because oftentimes I think it's optimized for the shorter.
Yeah.
GPUs are optimized for the shorter.
I tried. Yeah, I definitely tried both. So it's a lot faster than NumPy. It just is. I actually wrote this, the Python binding stuff, Monday, I think, or Tuesday. I was like, I don't know if I'm gonna get this done, but I'm gonna try. So that's what I did. Okay. So let's.
Thanks, Taylor.
Yeah.
Yeah, that helps.
Thanks. Yep. You're welcome. So the next thing is, so let's ask ourselves, what makes Python and C++, what makes this incredibly difficult? Well, Python users are super demanding people. Like, they have all these ridiculous types. They have ints, and if they don't want they create variables that are ints, then they change their mind all of a sudden, and now they're floats. Well, there's int 64s. And so when you're building a library, you have to basically write in C++ is a static language. So you have a static type language. So you have to basically write functions for every one of those types. That's a lot of typing, and I'm a lazy guy. So the question is, how does TensorFlow do it? Anytime I hit a problem that's really tough, I ask myself, how does TensorFlow do it? I have no idea. I made this stuff up. I'm thinking TensorFlow might do this a similar way, but I haven't read the code, and I probably should at some point for some pointers. But the other problem is that these libraries, when you write templates into them, they discard the templates. It's just, but you can do some interesting stuff. So I'm going to basically, I don't know if I should go over this now, or if you guys understand what I mean, that templates go away when you're compiling libraries. But a show of hands, who wants me to go over this example to kind of demonstrate why templates don't really work when you're using libraries? Okay, a few. Okay, don't be shy. Great. I'll basically show. I'll go over this quickly because it seems like most people understand that in examples. So essentially, I have. Let's zoom that in. So essentially, I have a really simple thing. So I have a header file, it's a template, and then I have a different function that has an explicit prototype. And then here, this is going to be my library. And in my template that is fully defined, fully specialized is what they call it, I will get a function in the library that compiles. And here, I will also get a function in the library that compiles. But if you were to try to use, go back to this header file, and try to use a template that doesn't exist, that's not in the library, it just fails. What's wrong with my thing? Stuff. Come on. Ugh, it's just that timeout. What's going on? That's not good. What the hell? Alright, I'm just gonna close this out. I don't know what's going on there. So hopefully it's all that. Okay, let's try this out. So I'm just going to run, so I'm going to just basically show you main. So essentially, because we only defined our fully specialized template for int, and we only specialized a fully, we did an explicit prototype and instantiation within the library for a double. This will work, that will work, this float will not, and this will work. So that's really all my entire point. So I'll show you if I compile the library. And I bash, let's see, bash main.exe.sh. And it should fail saying that it doesn't have a symbol. Now what's really cool is I also made a cool little script for demingling stuff. And as you can see here, we actually have a print INPL and we have a fully instantiated .int, but we do not have anything that allows us to do any template stuff in this library. Okay? So that's my point. Now the thing I think a lot of people do when they make their own ad hoc libraries is they probably use copy and paste and semantics, and they basically just define that function in every single type. We don't want to do that. So I'm going to show you how to avoid that. All right, so let's jump into the first problem. Is basically how do we actually compile CUDA with C++ 2A. I'm not going to go to that thing because I don't want to have, not have time. But the idea is simply we do two-phase compilation, where we basically create a wrapper lib that will be compiled with CUDA. So that will only be C++14. But we also have a second compilation phase where we link the CUDA stuff into the into the C++2A executable. And the only thing that we demand is that wrapper HXX is going to be compatible with the C++14 that CUDA uses and the C++2A stuff that you're using. That's the only thing that is required. So basically, what are we going to try to do when we build out our ++2A CUDA library? Well, we're going to basically do device pairs, which means we can get stats on our GPU. We're going to do large vector addition. We're going to do dot products. And I'm going to show you basically how the map and reduce concept. Now, let's kind of get into the project a little more. Let's get a little intimate with this. Let's see what's behind the hood here. So basically what we're doing is, it might include, I have a really interesting way. I like to do things by convention. So basically these files I just throw in just get picked up. But let's show you a spec file. We'll do the dot product. And with the dot product, this is all compiled with the most modern version of 2A that you can get, or some experimental version. And so here what we're simply doing is we're taking in this HXX header file, which is compatible with the CUDA compiler, as well with the modern stuff. And we essentially just basically call into what we want. Now this can be anything. This can be a float, this can be an int, this can be a double. I've basically defined this library to work with basically all the primitive types. And the types that we're basically compiling for is right here. I made it into some macro. So the 8, 16, 32, so you can, all that stuff. So our library will work with all that. Now obviously, in the copy and paste semantics, you have to define a function for each one of those types. But we don't. Instead, what we do is, let's go into the dot product. We actually have this function. And so it kind of gets a little hairy here. We basically take, and let me do a split on this. We basically copy and paste these macros for all these types and creates essentially like a type list, if you will. This primitive underscore types. And basically what it does is it defines some operator overload, and it expands and it expands and defines essentially an operator for each one of those types, whether it be an int or 16 or 32 or float or double, whatever. And so this is kind of an interesting but really bizarre way of hacking around the compiler to get it to do what you want. So before I go a little too far, I want to see if I got something in my slides that I forgot to go over. So yes, we talked about a little bit about what we're trying to do is, modern C++ with CUDA. So I don't know if you guys want to go over essentially the CMake file, but I'll go over it a little to kind of show you how the CMake file looks. So the thing about when you're building CUDA with CMake, it can be pretty difficult to kind of understand and get this all set up. But CMake actually understands certain languages like CUDA actually, and so it will know how to compile your CUDA projects if you include a CUDA language. And what we're doing here is that we find some CUDA package, and it basically knows where the libraries are, it knows where your header files are, So when it basically builds out that make file and compiles it for you, everything's just going to go off without a hitch. I also used Boost. I used two things in Boost, which is really cool. The regular system libraries for Boost and the Python 3. If you're making Python bindings for C++, Boost Python is pretty cool. It can also include NumPy calls, so you can actually call NumPy within your C++ stuff. The other thing that I want to point out is here, we're actually creating a library. The wrapper lib, I basically just do I like CMake top files, so I just simply recurse and find every single file that has a certain pattern, such as a .cu. And so I know that's going to be my CUDA files. I then basically just add it to a library, and then I compile the library, and then eventually that library is going to then be linked against the final product, which is going to basically be our tests, so our g-test. So I'm using g-test as our proof of concept. Okay, I'm going to stop for a second. Anyone have questions or concerns? Am I wrong on anything? Did I mess up somewhere? Because if I'm full of it.
Why did you put CUDA in a separate library? Didn't you just build it with the project right away?
Yeah, so I wrap all the ugly CUDA C++ 14 stuff I don't really care about into a library, because later on, if I want to use modern C++, then I just simply link against it. And so you can't use, if you're going to compile it in the same project or the same library, you can't use any of the modern C++. So you have to basically do it in two phases. So that's essentially what I did there. Anything else?
Taylor, if people are interested in finding out more later when you're done, I think you shared a blog post with, will you share that with us? And then also maybe your GitHub project.
Yeah, I can share my blog post, my blog post and my GitHub project. Yep,
Awesome.
Absolutely.
Thanks.
So we'll just kind of move on. So let's talk about, all right, what's the next thing I want to talk about? We can talk a little bit about, so the CMake, so I already talked about that. So let's talk about kind of the template metaprogramming stuff that I had to do. The compiler loves to basically throw away your stuff. It doesn't like junk. It optimizes things that it doesn't think you need. So in this dot product thing, you would think that it's enough to basically define a instantiation of the dot product IMPL. So I'll show you. I'll do a screen split, and we'll do the dot product. And so essentially, what we're doing is IMPL, I believe, is what calls into, let's see, I gotta remember what I actually did. So it creates something called product CUDA. That's what actually does the GPU computing stuff. Dot product IMPL is not what you're actually going to use. You're going to use this interface called dot product. Actually, oh, I see. That's what I did. Okay, cool. So here what I did is I essentially said, okay, we're going to create a usable, essentially a usable structure that has a callable operator called dot product, and it's going to basically inherit from this structure called dot product IMPL. And what dot product IMPL does is it expands everything. And so let me kind of write on the board. Do we have the marker? What it kind of does?
I think it's by the window.
Oh, cool. So I think the template stuff is really quite confusing unless you actually write it out sometimes. So we have a template, thank you. And we basically have a class A, I think. Yeah, and a class, we'll call this AS. And this basically just means, this 3 dots just basically means that I have a whole bunch of types that I want to expand. And so it will recursively call itself. And we have this using directive that basically defines some prototype. Dot product INPL. And what it does is it only passes in, you guys probably can't read that. That sucks. I have to let it go. So pretend I just wrote all that stuff, but what it will do is we only basically pass this guy in, because what happens is we have this using operator that's going to be what actually calls into the CUDA stuff. It's going to recursively call this template, and it's actually going to throw away this class A. And essentially what it kind of basically just does is magically it creates an operator, a callable operator with every type that we're interested in. So it will call something with an int, it will call something with a float, it will call something with a double. So basically every single thing in the primitive types list, it basically defines a prototype for that operator. And that's really cool. But the problem is that, you know, that's not enough for the compiler, okay? What's going to end up happening is that when we basically call into our library, we want to basically define what this type is for that operator. And so we only use this T type, because that's going to basically be the function that we are calling the type for. So what we're kind of doing is a weird way of shortcutting, and we're basically kind of weirdly defining every single primitive type in that file or in that library using this weird template trick. And if you basically compile it with all those types, it makes sense to the compiler, and it can actually build your library. However, the problem is that that's not enough for the compiler to keep your it's not enough for the compiler to keep your function. If I remember, I believe the compiler will throw out member functions of structures unless you use them. And so I designed this hack that basically calls every one of those different types with BS values. And so the compiler thinks, oh, well, you're using it in this library, therefore I should probably instantiate it because, well, what if they don't have hack.dot product? Well, that sounds like an important function, so maybe we should actually build code for this implementation. Okay? I hope I didn't lose anybody because I almost lost myself. Are you guys okay?
Say, Taylor, which compiler are you using?
I'm using Clang. I'm using Clang 7. I've also, this project works with GCC.
It does? Okay.
And then the third compiler that's being used is MVCC. And that's what actually builds your library. The wrapper library that allows you to call into CUDA or your GPU. So this stuff is like really complicated. Honest to God, guys, like template stuff is another world.
So isn't this just loading your library with a whole bunch of methods that you may or may not ever use, or your customers using the library may never use?
Absolutely. And actually, you know what? I think that's okay in some ways. If you really want, they can recompile it with different primitive sets, so that will slim down your library. All you have to do is essentially go to this file and take out whatever primitives you're not using, and then recompile your wrapper loop. And that'll slim down your binary quite a bit. But unfortunately, yes, you have to kind of load that. You got to crack some eggs to get it on, basically. So, yeah.
When you say library, is this static or shared?
This is shared.
Okay.
This will work with static and shared, but when you talk Python world, they demand shared.
Yeah.
Yeah. Anything else? Okay. Let's see. I lost my train of thought. But let's go back into this stuff. So a lot of you guys are here because of CUDA. So I'd like to talk a little bit about CUDA now. So when you're working with the CUDA world, you're talking about, there are two very important concepts. You have a host and you have a device. The host essentially is what's on your computer. It's the RAM, CPU, it's all that stuff. And then the device is really just the video card that you're doing your compute on. So we always see interesting directives like global or device or host. And so let me show you something, is we have this directive called global. This global basically is saying to the compiler, hey, I'm device code. You should probably throw me onto the, into the device so the host can call me. So this is known as a kernel. And what we end up doing is this memory that you see here, this pointers, this is all pointing to actually GPU memory. It doesn't point to host memory. None of this stuff does. You can't call this from the host directly. And so that's kind of interesting. So in old CUDA, you have this thing, you have your host memory and you have your device memory. So the way old CUDA basically works is that you basically have to build out your memory on your host, and then you have to do a special thing called a CUDA copy that will copy that into, it will send data over your bus into your device, and then when that happens, then you can then run a kernel. So this CUDA malloc, now this, let me explain this -r, this probably is confusing. This is just some easy function I made that basically just prints out errors. You can ignore it, it's not like anything interesting or standard. But what I did here is I essentially said, okay, I'm going to create two types of basically CUDA memories. Well, actually 3 types. So we have a vector A, vector B, and R, which is your result, right? Then what we're going to do is we're going to tell CUDA, hey man, I got something I want to do. Can you allocate a lot of memory for me? And it's going to say, sure, Taylor, just use this function, CUDA malloc, and just tell me, what's your pointer, and tell me your size. So the sizes are always in bytes. And then there's an operation where we then basically copy that memory. So we're going to copy some memory. So AI is what's host memory. So before we call into this function, we've already allocated basically two memory arrays, AI and VI, and then we also allocated RO, which is just a scalar. It's not like an array, it's just a scalar. And this is where we basically want to read from and also write to at some point. So when we're basically saying, I want you to take data that I've allocated, I want you to throw it into the into my video card, you're going to give it the CUDA pointers, and you're going to basically use this, this variable CUDA mem copy host to device. And you probably are wondering, like, well, is there another one, like device to host? And yes, there is. The next piece is this, is where we're basically, is now that we set up the memory for our CUDA to actually execute its program, we now need to basically tell CUDA or the video card, hey, I want you to execute this function, but I'm going to give you a configuration. And so the configuration is going to basically be this grid size, block size, some other stuff. So we can kind of get into that now. Now, I'm also going to talk about this. This is just a regular template. C++ 14, CUDA will support some templates. So it does support templates. So I kind of use that because it's actually quite useful. What's really cool is that I can compile. So the functions that I want to define, its data type has to match what's in CUDA. So it has to also match the CUDA type. And so basically I just create a template TR, and then it basically will define those kernels for those types, which is really useful. So let's talk about grid size, block size. Now there's a cool little graphic that I bookmarked before I got here. Not this guy. Let's see, CUDA memory. This might be it. So this might actually have grid size and block sizes. So let's talk about this a little. All right. So CUDA GPUs work in a, they're called single instruction multi-threaded devices, right? So the way that you think about how things happen within CUDA, it's totally different from basically your CPU. Threads live in what's called a warp. So warps are normally 32 threads, and they all execute the same instructions. And that's how you get this massive parallel compute power. And so when you basically say, I want to, in fact, I don't like this graphic at all. CUDA, memory, blocks, warps. Well, I reinvent the wheel. I did not make a little infographic for this, right? So yes, we have, this is like the perfect infographic actually. Hopefully it's, yes. Ooh, this is great. So what happens is when you set something up, you basically have hierarchies of memory. You have the warp, which is the lowest unit of number of threads you can tell your kernel to run on. You have a block, and a block is made of a number of warps. And then you have a grid, which is made of a number of blocks. And then you have multiple grids. So there are basically several different configurations you can run. So if you're running a dot product on something that's like an array of 1024 elements, you can break that problem down. And in fact, what you do is you would basically divide 1024 by essentially the number of warps in a block and grids. So basically, let me see if I could, I don't know if I want to write this on the board, but what we do is we basically have an element in each. So let's see if we have dot product CUDA visual image. Yeah. So what's happening is basically, come on. What? It's like they're the bait and switch.
If you right-click the image, you can open.
Yeah. So let's open the image. Oh, whoops. Oops. Screw it. Hopefully, if I just do that makes it good. Oh, this is actually a better version. So basically, what we're trying to do is basically what you see here. Let's see, open view image.
That's what I call an agile presentation.
Yeah, you gotta go with the flow. And then what I do is I go to my downloads, and then I make that big. That's easy. Cool. So this is what we're doing today. Is when we do a dot product. So each thread has like a thread index, right? And that will act on a particular element. So we have two arrays, A and B. And so each thread is going to add the elements within that index. So this would be thread 0. So it's going to add element 0 of array and element 0 of B together. or multiplying. It has to multiply, and that's a dot product. And then it's going to basically do that for every single element within that array. Eventually, what will end up happening is if your threads do not line up perfectly with that array, you're going to basically have to go and shift an entire grid over, or you're going to have to shift your frame over, and then do the same thing. It's a lot of writing on the whiteboard that I don't care to do. So, but bear with me. So let me show you exactly what that means. Yes.
Quick question. Is that what that built into CUDA so I don't have to write all the math?
It sure is.
Okay.
Yeah, sure is. Yeah, you have so many good libraries. You have CUDA, you have the linear algebra libraries, you have, you have all sorts of different libraries that already do this. But then what would we learn, I suppose? So you do it for the learning experience. So to compute what elements you're going to multiply A and B within this CUDA memory, we have to compute what you call, your thread index. Now, you also have different types of memory. You have things like local memory registers, you have shared memory, you have global memory, you have device memory, all these different memories. When you're new to CUDA, it can be really confusing. The memory that I have here, int I equals index, it's either a register or it's local, I don't know. But what's important about this is that it's private to this thread. No other threads can see things like index or stride. Also, what's really important is when you're talking about memory access latencies, you want to make sure that you're doing what's called on-chip memory access. So local memory access is actually slow because that's considered off-device. Registers are way faster, but you don't have a lot of them. Whatever doesn't fit in registers overflows to local.
Is that local to the GPU or local to the?
It's local to the GPU.
Okay.
Yeah, it's like in, I guess, like this global, this space in the GPU somewhere else. So here we're just simply multiplying all the numbers, and so that goes into some array. Now the next thing we got to do is we got to synchronize the threads. So where's that marker I put here? So we have A and B, C and D, and we'll do it with basically A star, B star, C star, and D star. So thread 0 will multiply these two. Thread 2 will do that. Thread 3 will do that. Thread 4 will do that. And then we have to basically, when the results are done, we're going to basically put it into some result. We'll call this result A, result B, result C, and result D. The next step is we need to basically wait for all the threads to finish. Wait for threads to finish, because the next step is we have to add all these numbers, which creates the dot product. So what we can do is we can do something kind of tricky. We can use one thread from our warp or one thread from our block or something to basically add these two numbers up, but the other threads will do nothing. So we can basically just simply add these two guys up and stick it into some memory. So this is kind of the reduction part. So this is basically MapReduce. And the function that basically says, hey, before you start adding up all these values, thread 1 or thread 0, I need you to wait for your other threads to stop. Otherwise, you're going to get bad data. You do that with what's called sync thread. Sync thread essentially is a call that says we need to stop once we get to this point. So that's what that does. And then I have this thing called thread IDX. IDX, I believe, is going to be redundant in different blocks, if I'm not wrong. And I think that is correct. So we basically say if we have an X index of 0 and a block of 0, then I want you basically to aggregate everything into one value. In this case, actually, I only use one thread out of all the blocks. So only one block, one thread is actually adding up all those numbers. Any questions? And I did that for simplicity, not because it was a better design.
But you said there were 32, correct, in the block? 32 threads?
Yeah, 32 threads in a warp, and then you can configure your block to have as many warps as you want. So it's one warp will perform this instruction of adding all the results into one spot.
Now, is that true of all, of just the newer CUDA cards that have the 32 threads per warp?
All CUDA cards have warps. Some will have 32, some could have some other number, but my particular device has 32 as a warp.
Are there tools to help you explore your hardware to understand?
Yeah, they have example programs you can run. Unfortunately, that's pretty much the limit as far as I know. So I run example programs that I compiled in CUDA that tells me everything about my device.
Okay.
So rereading this code, I lied. Reading this code, I lied. What we're doing is one thread within the block is adding everything else up. So there could be 256 threads in a block. Only one of those threads is adding everything up for us, and then putting it into some spot. And so that's going to basically be our array. So the resulting array will basically be the number of blocks that we have. So this could be B0, so this will go into B0. This will go into B1. And then, B2 and B3. If you have more threads. All right, so when that is done, and I'm not going to talk about warp divergence. When that is done, we do this thing called the CUDA device synchronize, which means, are you finished with running this kernel? And if you are, basically you can continue on, otherwise you're going to wait. So this is a blocking operation. The next piece is, what we're going to do is we're going to create an array that's going to basically fit the results of this CUDA memory back into the host. And so we basically do a memory copy from device back to host. And then we just simply sum up all the elements. And then we free our memory because we're nice. And then we basically write that data into whatever hell mutator I gave it, which is this guy at the very end. So we expect this to have new value now, in reference, and then we basically return a CUDA status. So that's basically how this CUDA stuff is kind of working. It's a lot like when you first kind of get into it, but once you kind of work with it more, it's not so bad.
So Taylor, how does the answer get back to the host?
So we write the data. So CUDA will have a special place for the result that we've allocated, and we write that data onto the CUDA memory device or the video card. And then what we do is we wait for the program that's running on the device to stop so that we know we have the final result. And then what we do is we allocate some memory on the host, which is going to be on the regular computer, and then we write that memory to the host. So that's what that's doing.
So the GPU is pushing the data back, the host is not pulling it.
Yes.
Right.
Yeah, so the GPU actually pushes that data back into the host. Is it full? Yeah, it's a mem copy. Exactly. So that's what's happening. Okay, so that's pretty much all there is really to this CUDA stuff that I have. Something that's really cool is we can profile, and I've already basically built out all the things that I'm interested in. So we'll basically run an MD profile on something, and we'll do it on the dot product. Because that needs a pseudo for some reason. Stop. It's gonna do it. It has its own mind, so it's gonna do it anyway. But when it behaves, yeah. Question.
Yeah, I was wondering if all the operations are blocking.
Are they blocking? Probably, is my guess. Yeah, I would imagine so. I know that with CUDA, so this is a side project. I don't get paid to do this, but from what I understand, with CUDA you can write to memory asynchronously as well. Everything I'm doing here, I believe, is blocking, but you do have like data streaming to the GPU, and then it can kind of do its thing and then write things back. But that is like a whole new basket of berries or something. It's just like crazy. I haven't done anything like that, so yeah, this thing is not being cool. So let's just close out. This power cycle that happens. Object. So we're going to do a pseudo in the profile of build dot product. Yes. Okay, cool. So now we can kind of take a look at the breakdown as to what's taking the longest. Now, obviously, when you look at things like it's 755 mics for a CUDA mem copy, you're going to laugh and like say, well, of course, NumPy is going to be faster. NumPy probably does things like vectorizations on the CPU, so it does all that stuff. So for something like this, or a simple dot product, you're probably not going to use CUDA. But for like really complex things like nomads, probably definitely. Some things that's kind of cool is there any interesting things? So my kernel apparently runs in 159 mics, which which I think is slow, but yeah. So you can get like a really cool breakdown of all the stuff.
And what was it that you ran there?
So it's an NVIDIA CUDA profile. So NVIDIA, when you build with its libraries, somehow it figures out how to run stats on it. It's its version of, I guess, PERT or whatever. So it's pretty cool stuff.
So you were demonstrated 1024, right? So how large of a data set can you put into there, and how can you determine, right, what number you got in the GPU that you're trying to slam data into that?
Yeah. So okay, let's find out. Let's do this by an example. We have CUDA ops, which is essentially my thing, and I don't know. Okay, so it gives me a warp size of 32, peak memory bandwidth. That's how fast I can write. Actually, let's try this instead. I believe there's a. I got a figure. Where's my CUDA path? I always forget this. Which NBCC? Okay, perfect. I believe this might actually have examples in it, so I can tell you how you can find out. You know what? I don't know where that example. Do you guys see something that says examples?
There was samples.
Samples, that's it. And then there is, I believe, something
Extras
in
as well.
utilities. And then device query is query. And then, oh, I didn't make my samples. Oops. compile it. Let's see. Okay, if this compiles, dangerous, right? This probably needs to too, so why not? Okay, cool. So this is really cool. So, GPUs will have, like this cache memory, which is super fast. But the thing that's interesting is you will need, there should be something here that says how much memory, but you basically have a lot of global memory. And sometimes it could be like 3 gigabytes or 4 gigabytes. My Titan X, I believe it's like 16 gigabytes, so you can throw in 16 gigabytes of data into the GPU, so it can get quite large. But if you're not careful, you will get memory errors, runtime errors, and so I can actually even demonstrate that because I have poorly written code. But it's but yes, you do run out of memory, but you can get quite a bit of stuff in there if we have a lot of dash, so a lot of money. So
So what you're showing, though, at least for me, Taylor, is because I'm new to the CUDA and playing around, you're showing us and I think there's a lot of novices here.
yeah.
What tools are available and how to use them to explore your system. So that's great.
Yes,
That's useful.
absolutely. Yeah, thank you so much. Yes, GPUs have a lot of global memory, so that's where most of the memory is going to probably end up. Anything that it uses, I imagine they have temporal and locality caching kind of. I don't know enough about GPUs in particular to tell you. And keep a straight face, but but yes, you do have some GPUs have enough memory like your computer, so it's pretty cool. Let's see what's next on the agenda. Gotta go back to my slides. That's cool. Already went over that. Already went over that. So I guess the next thing for us is how the hell do we integrate this with Python? So given that we actually have a CUDA library that works that we can link into modern C++, maybe we create a, we do like 3 phases of compilation or 1 or 2 phases, it doesn't matter. But let's see. Ooh, should have done C back. Let's do this. So Python, oh yeah, that's fine. So I created something called CryptMax. That's basically my thing. And we create something that basically calls from Python into C++. I know a lot less about this particular thing because I did it Tuesday. But what's really cool is that you can wrap objects into Python objects, and that's how Python interacts. And you can extract values from the Python objects, use it in the regular C++ world, and then basically wrap it again and put it back neatly. And here I basically implemented a Python module. And the way you basically create your Python module, it all starts off with this little piece of magic called the Boost Python module. And this is, by the way, it's all, this is the Boost Python library. And you initialize Python. If you're using NumPy, you also have to initialize NumPy. And then basically, when you import this module, you're going to get these 3 really cool functions, nifty little functions, the greet, the dot, the print flat. Print flat basically just simply says, hey, I have this NumPy array, I want you to print it in C++. That's all that does. And I want you to print the type. So that's what that does, and greet is just hello world. And so basically I just simply built out void functions that take in things like a NumPy array. And you have to use, this thing called Python extract. This is part of the Python Boost library. And you can extract things like attributes. like the number of dimensions from your array. So, number arrays are basically tensors essentially. They can have several ranks. So this could be matrix or like, a matrix within a matrix or however you want to call it, shapes. So this stuff is pretty much straightforward. Here I kind of followed the compiler. I didn't want to do anything too fancy, so I didn't do any crazy template kind of programming here. Basically just defined stuff at runtime, and it would basically call into my library. And you can see that in this dot product, where essentially all we're doing here is we're essentially creating some Python wrapper function that's going to, we create a kernel configuration object structure with a block the size of the grid, and we basically call the dot product with the kernel the size, and then we basically just, send in our data arrays, and hopefully we get some result, and then we drop the result in the Python object. This is like the easiest stuff of everything I've done so far. So making something that's fun and easy for users who don't like C++ and want to just use Python for some bizarre reason, you still use your library, which is really kind of cool. So, is there any questions that you guys have?
I have a question. So you need to basically customize this for the video card you're using. You can't. Is it possible to write a generic one program to do what you're doing here that will run on a whole variety of different video cards?
Yeah,
which have different memory sizes, and do it in a generic way so that you don't have to look it up and say, what's my memory for this particular card on this? If I want to make a generic program that does what you're doing, how do you do that?
I would imagine what TensorFlow does is that it does a device query. And I actually wrote a program that uses, you have API calls where you can call into CUDA and get the specs on your device, so that you're not going to have memory, you're not going to write out of memory and things like that. So a good programmer would actually do that device query, and they would basically write code to be more robust, as you mentioned. As far as compiling, you're going to use different compiler flags for different architectures. You have something called like SMArch. You have different types of CUDA. Let's see if I don't remember what the flags are. But maybe I can find what those flags. But those flags will basically configure for the correct device.
Okay.
The correct architecture.
And the second question with that is there a way to ensure data alignment from your host and your device so that you're filling in these blocks or waves or whatever you're calling them in the best, most efficient way?
It's a really good question. I actually haven't ran into issues with any kind of data alignment. My guess is it's done under the hood.
Yeah.
I don't know if if you're doing some freaky easy stuff, then maybe that will be an issue you run into. But I think I've seen maybe directives or something that basically aligns memory for you for CUDA. But honestly, I've never done anything like that, so I wish I could tell you.
Okay, thanks.
Mm-hmm.
Do you feel like this is a stopgap measure waiting for NVIDIA to ship like a C++ 20 CUDA compiler, or is NVIDIA going in a different direction than C++ 20 is going? We'll always have to do this to use GPUs with modern C++.
Yeah, I wish I worked for NVIDIA, but I'm just a fan in the fan club. But I would imagine that I would hope that if they want more adoption, they will continue to modernize their compiler. When I first started, they didn't have C++ at all, and now they have 14, which tells me that they're going in that direction. They're going to modernize their stuff.
Yeah, so platform. So the Kronos group, they're like a standards group. They came up with 4GL. They recently come out with Vulkan. It's supposed to be the new GL. Vulkan's a lower level pipeline approach. Those are standards. The NVIDIA cards will support those also. So you can use CUDA as an API, or you can hit Vulkan or something else directly that sort of needs to be standard. And then some of the GPU, the general purpose GPUs, there's a consortium of companies, including NVIDIA and AMD, those guys, that are standardizing general purpose computing on the GPU. So that's the GPU. And Bitcoin can't drove that a lot. So there are libraries out there, but if you hit the Kronos group, you'll find the top 3 or 5 libraries that are C++, modern, cross-platform. The only other comment I thought I'd throw out there is every device needs its own alignment requirements, like 24-bit alignment or 2-bit or whatever it is for data types. So the APIs, when you create your buffer, you'll have to fill it in aligned the way the card wants it. And usually interacting with the card will do that. The only other thing is, because I thought you did a really good job saying host memory, device memory, and you have to marshal that across. So you only marshal across what kernel fed. So you have to interrogate the card. If you want to make allocators or some higher level thing to do that, that's fine. But you will allocate it, you will align it, you will copy it to the card. So the numbers here, contrasting between the Python and the NumPy, the Python NumPy and C++, you essentially show that's the cost of marshalling. So the big bang for the buck is if you set it up, shove it in the card, and then you have it do like a bajillion computations for the next hour. You're not pulling anything back. That's like the ideal scenario, or that it's out of band coming back to the computer to refresh the screen while it's still crunching away. That would be the ideal scenario. So alignment and memory allocation, you'll actually have to allocate, get fail, didn't allocate to, you're gonna have to handle the out of memory issues yourself. So writing allocators. So.
Yeah. Thank you for that comment. Very thorough. Yeah.
Was there some motivating C++ 17 or 20 feature to doing all the work for not just using C++ 14 all the way through?
Motivating feature, I don't know, there's probably some cool syntactic trigger or something I probably would have wanted to use. I can't name it off the top of my head, but I think, I've done things with I guess maybe lambdas, there are certain things you can do in 17 and 2A that you can't do in 14 that bothered me. Things like that, I suppose, because I'm so used to working in really modern stuff that I kind of missed. But there's not like a really good motivating factor other than I can kind of do it, so it's academic. Yeah.
So, about the mixing of C++, 14, 20, continuing on the subject, I guess. So when you say, for example, we saw a file that has the kernel global function that actually runs on the device. And on 20 lines below, there was a C++ that function that actually ran on the host, right? NVCC is, I don't know CUDA that well, but compiles that part, and I'm assuming it just redirects to Clang or something in C++ section to the Clang, and it just compiles the CUDA kernel one itself, because Clang doesn't know how to compile CUDA. But I would assume, why they don't just the normal host device host C++ just compile with C++20, why do they care?
Yeah.
It's a standard C++ function call standards. And for Clang, they don't change it anyway. So why can't we use MVCC with C++20? I don't see a real technical reason why just forward it to Clang. real CPU running code to the Clang and just compile the CUDA section. Or, worst comes to worst, can't I just write the device code on a separate CU file and write all my CPU code on a normal C++ and compile those C++20, and it's just a function call, and you don't even call that CUDA function directly from the CPU, it's just you call a CUDA API, run that thing I just uploaded.
Well, okay, so yeah, part of the motivating, yeah. Let me see. Let's see.
Or I think that they don't have a parser, a C++ 17 parser in NBC.
I think that, I mean,
Yeah.
I don't understand why for NVIDIA, such a resourceful company, just use Clang or something.
Yeah.
Anyway.
There is preliminary CUDA support inside of Clang, so Clang might be better than MVCC at some point.
I wouldn't be surprised.
Yeah, as you know, as I said, you know, the original motivating factors, I didn't want to copy this.
I can understand that section to be
Based
C++
on
14
Yeah.
limited,
But
but I don't understand why the bloat is limited.
yeah, it's probably the reason that Lenny's out. So.
Yeah.
He's a very smart guy, so I'll take it. That's probably the reason. I don't really have anything else. Any other questions you guys have?
There was a lot of specialization for the dot product inside of your template. Like that template seems very focused upon the dot product. Have you considered a way to, like, for a template within a template for passing in a function that you want to be specialized with all those arguments?
Sorry, what? So you're saying that I don't think I understand. Well, what you.
Is it possible to pass a function as a template argument and then have that template function specialized by several of the types?
I've never tried. Maybe.
Oh, okay.
I'm sure there's a lot more you can do. I don't know the answer to that. So.
Thought I'd just suggest.
Yeah.
Taylor, could you also maybe just show your blog post or point in the direction?
Yes.
And
Yes.
your GitHub.
Yes.
In case people are interested.
I think I'm a better. I hope I'm a better writer than a speaker. So, I have this blog post, and it kind of goes over a lot of the stuff that I basically mentioned in this presentation, and I might as well just log in a Meetup right now and just paste it. So you guys have a little something you can take home. Special gift. Comments. Here we go.
Awesome. And then maybe your GitHub.
Oh yes, the GitHub. Absolutely. And then GitHub. So, and then I kind of want to make just like some fun announcement. If anybody just wants to, just get down and do something kind of like crazy and build some math library with me, I always maybe I'm trying to do some more collaboration with the work I do because it keeps me sharp and it always helps to get other folks into the thing. But the library Atomics is essentially going to do physical chemistry computations, so we'll do things like Hartree-Fock approximations and things like that. So if you have an interest in physics, hit me up and hopefully we can chat.
Awesome.
So.
All right. Any other questions?
One more thing I want to mention, there is in the CPP Connect in the second week, there's a class CPU to GPU computing given by one C++ committee member. Michael Wong. So there is a class that which I'm attending. You can take in C++ Con at the second weekend.
All right. Good to know. All right.